Hi, in this video we are going to build a bug simulator in Blender using geometry nodes. These bugs will crawl around your scene and react dynamically to lights, moving away from illuminated areas. Let's dive in and build it from scratch. Here in Blender I have prepared a simple scene with a few objects to act as the environment. I already put them into a separate collection. I switch over to the geometry nodes workspace. I have the geometry node editor, spreadsheet and the 3D viewport open. To begin building the bug simulator, I add a new mesh object to the scene. Since we don't need any existing geometry, I jump into edit mode and delete everything, leaving us with an empty object. I press F2 to rename the object to bug simulator. Make sure that the object is outside the environment collection. Next, I create a new geometry nodes modifier and name the node group bug simulator as well. We won't be using the default group input node, so go ahead and delete it. Now let's spawn the bugs into the scene. First, I drag and drop the environment collection into the node editor. Set this to relative. Since this collection is brought in as instances, we need to convert it into actual geometry. To do that, I connect a realize instances node. This gives us access to the actual mesh data. To create our bugs, we'll start by scattering point across the environment. Later, we can turn them into bugs. So, I drag from the output and search for distribute point on faces node. Before we go further, make sure all our environment meshes have their scales applied. I select them and press Ctrl A, then choose scale. This ensures that the point distribution behave consistently across all objects. To preview the scattered points, I add a viewer node. Right now they are hard to see since they blend into the scene. So I select the bug simulator object, go to the object properties and change the viewport display color to something more visible. I'll use a dark orange. Then in the viewport shading setting, I switch the color mode to object. Now we can clearly see the scattered point across the environment. I also pin the geometry nodes editor to keep it locked while working. And this is all for point distribution. You can control how many bugs appear by adjusting the density value in the distribute points node. I keep it like this and hit Shift P and frame these three nodes. Label them distribution. Now let's get these bugs moving around the scene. Since we are doing a simulation, I start by adding a simulation zone into the setup. I plug our points into the simulation and plug the simulation out to here. To ensure the bugs move only within the environment, we'll generate their movement direction based on the geometry of the environment itself. So I duplicate these two nodes to get a reference to the environment. Then I drag from here and add a geometry proximity node. This will calculate the nearest point on the environment for each bug. But if we distort the sample position slightly, the bugs will try to move towards a nearby random location instead of always going to the absolute closest point. To add this distortion, I start by adding a position node. Then I use a vector math add node to modify that position. To generate the random offset, I plug in a random value node. I set its min values to -1 so it gives us a full range of direction in 3D space. This is probably too much, so I add a vector math scale node between and set the scale value to something like 0.05. This value controls how far each bug is willing to look around for a new position, essentially acting as their search range. At this stage, we are just identifying the target locations. To actually move the bugs towards that point, we need to calculate the direction vector, which is the difference between the target and the bug's current position. So I add another position node. This one represents the bug's current location. Then a vector math subtract node. I plug the destination position into the second input. Now we have the direction vector. To move the bugs, I add a set position node inside the simulation zone and connect the direction vector to the offset input. If I hit play, bugs will start to move around in the scene. You will notice that some bugs might fly off into space. We'll fix that later. For now, let's make their movement feel a bit more organic. To make their direction change over time, we animate the random seed. I plug a scene time node and connect the seconds output to seed input of our random value node. Add a multiply node in between. Plug a random value node to it and set them to something like 0 0.1 and 3. Now each bug changes its direction at a slightly different rate. The bugs are still moving a bit too fast for my liking, so I insert a scale node just before the set position and set it to 0.3 to slow things down. That feels much better. Let's frame these nodes as well. I label it movement. Let's make sure the bugs always stick to the surface of the environment. I duplicate this set position node and place it here. Then I paste the two nodes we used earlier, the collection info node and realize instances node, to bring in the environment geometry once again. Then search for sample nearest surface node. I switch the data type to vector since we need the position of the nearest surface. So plug a position node to value. This will continuously project each bug back into the environment surface. Just like that. Let's frame this as well. Right now our bugs are facing through each other. There's no collision detection. So let's fix that by adding a simple avoidance system. If a bug sees another in its path, it will steer away. I'll set this up before the bugs are projected to the surface. Since we are adding another movement adjustment, I bring in another set position node. To detect a possible collision, we need to know which bug is nearest to each one. For that, I use the index of nearest node. This gives us the index of the closest point, in this case, the closest bug. To get the actual position of that nearest bug, I use the evaluate at index node. Plug the index to index. Set the type to vector and plug in a position node as the value input. We found the nearest bug. Now I need to find the distance between the two bugs. So I add another position node. This gives us the bug's location. To find the distance between these two, I can simply use a vector math distance node. This outputs the distance between the two bugs. We can use this to determine the collision threshold. For that, I add compare less than node. Let's set this to less than or equal. And I set the b value to 0.1. If the distance is less than 0.1, we'll consider that as a potential collision. This value depends on the size of your bugs, so feel free to adjust it for your scene. We'll use this comparison as the selection input for our set position node, so only bugs about to collide will be affected. To repel them, I duplicate the position difference calculation, change it to vector math subtract, and normalize the results using a normalized node. This gives us just the direction with no magnitude. Then I add a scale node to apply a consistent repelling force. I'll set the scale to 0.05 and plug the result into the offset input of the set position node. Now when two bugs get too close, they automatically move away from each other. Let's lower the threshold slightly to 0.05 to make the repulsion less sensitive. Currently this collision system updates once per frame. If you want higher accuracy, you can wrap this logic in a repeat zone to calculate collisions multiple times per frame. For this example, it's not necessary, so I leave it as it is. I set this to 0.025. Frame this as well. If you're not seeing the bugs in the viewport right now, make sure your output is connected to the group output node. Now let's make the bugs avoid the light. To visualize the effect, I switch to rendered view. I am using Eevee. I darken the world color a bit so the lighting contrast is more visible. Then I add a point light to the scene and set its intensity to around 100. I also enable custom distance and set it to 3 to limit the range of the light's influence. Lastly, I turn off ray tracing. These settings aren't important, they are just to help me clearly show the lit versus shadowed areas. So back in the geometry node, since I want the bugs to either move around normally or escape from the light, I make that light avoiding setup here. First we need to find which bugs should escape. I drag and drop the light object into the node graph and set it to relative. Blender doesn't provide any light related data via geometry nodes, but we can still work with what we have got. First, I need to find the distance between the light source and the bugs. Just like before, I use a vector math distance node to calculate that distance. Then I could use a compare less than node to make that threshold, just like before. But I want a gradual fall-off, where bugs closer to the light react more strongly than those further away. So instead of this, I use a map range node. I set from min to 1.5 and max to 3. This means bugs within 1.5 units start reacting strongly, and those between 1.5 and 3 have a smoother fade out. If I view this, you can see bugs that are inside the lit areas have that 0 to 1 gradient. But I reverse this by swapping these two min and max values. Like that. Now to use this as our mask for bugs movement, I add a mix node. Plug this to factor and change the type to vector. Black areas will have the A vector, so I plug our regular movement to it. B vector will be our escape movement. The mix node will now interpolate between the normal and escape movement based on the mask we made. I plug the results into the set position offset. Now let's build a vector that points the bugs away from the light. So here is our surface. This is our light source, and here I draw a bug. What we want to find is this direction, the one that goes away from the light. To calculate that, we need two vectors, bug to light one and the surface to the light one. We can calculate this first one using our bug's location and the light's location, but we don't have enough data to calculate the other. This vector is basically the surface normal. We know the direction, we just don't know the magnitude. In those scenarios where we know one vector and the direction of the other, we can use projection to find the third vector. So let's do that. I duplicate these two and use a vector math subtract node to calculate the bug to light vector. Then drag from that and search for vector math project node. To get the surface normal, I copy these two nodes again. Add a sample near surface node, set it to vector and plug a normal node. This gives us the surface normal. Then I plug that into project node. Now to find that third vector, I subtract it from the first vector. After that, I add a normalized node, follow it with a scale node. This will be the escape velocity. I set it to 0.3. Plug that into B-socket of our mix node. Now when I press play, bugs flee the light. I increase the animation range. In the wireframe mode, you will see them dynamically react. When the light moves towards them, they scatter. When it moves away, they gradually crawl back into the area. You can adjust the scale values to get the exact results you want. I frame these. Now let's bring in the actual bug model. I imported a cockroach asset that comes with a walking animation. When I play, you can see it keeps walking. That's because I've added its walk cycle into the nonlinear animation editor and repeated it several times. Now we are going to instance this model into our simulation points. I hide this in the viewport and go back to the geo setup. Right after the simulation zone, I add an instance on points node. Then drag and drop the cockroach model into the node tree, set it to relative, and plug it into the instance's input. And there we go, giant cockroaches everywhere. To fix the size, I plug a value node to scale, set it to something small like 0.05. Now they look much better. On flat surfaces, the bugs look great, but around curved areas like here on Susan, you'll notice they aren't oriented correctly. To fix that, we can use the surface normal and align the bugs to the terrain. So I duplicate this setup. Instead of sampling the position, we sample the normal. To use this to orient bugs, I add align rotation to vector node. Plug this into vector. I think the default axis is fine, so plug the rotation into the instance rotation. Immediately, the bugs now align properly with the surfaces they are walking on. They are sticking to the surface, but they are not yet turning in the direction they are walking. Let's fix that. So here we have the bugs movement, and separately we have the collision movement. Let's figure out their final moving direction from this. I drag from our mix node and add a normalized node to grab the direction. I can grab this direction from here, but I only want them when there's a collision. So I put a switch node here, plug this threshold to switch, and for the true socket, I plug this direction. And I will store the results as a separate attribute. Add a store attribute node, call it direction and set it to vector. Plug this to value. Then here I duplicate this align rotation node. Plug the rotation to rotation. Add a name attribute node and select the attribute we just created. I plug that into vector, and for this the direction must be Y. And there you go. The bugs are now walking in the direction they are actually moving, across surfaces, around collisions, and away from lights. Right now, bugs avoid areas even if they are in shadows. That's because we are using proximity to the light, not the actual light casting. To fix that, we can simulate how light interacts with the environment using a workaround inside Geometry nodes. So in the geo setup, I add a UV sphere. Set the segments and rings to the same amount. Drag and drop the point light into the setup to get an object reference. I want to assign the point light location to this sphere. Add a transform geometry node and plug this location into translation. I set the scale to about 0.1. Just like a point light shoots rays into the scene, I want this sphere to shoot its vertices into the environment. For that, I add a Raycast node. Our target geometry will be the environment. I get that reference from here. To shoot the vertices around, like a lamp, we can use the mesh normals of the sphere. So I plug the normal node to the ray direction. And for the ray length, I select the value we choose earlier for the light. 3 meters. I type that here. This way it shoots those vertices and gives us some results based on the hits. I put a set position node here. Grab from this hit position and assign that as the vertices position. Since I only want to distort the points that hit the surface, I plug this isHit boolean to the selection socket. I don't need the rest of the mesh that doesn't hit any surfaces, so I put a delete jump node here. Drag from isHit, search for not boolean math node to get the inverse of it and plug it to selection. Now we have basically created how the lamp casts light into the scene with a mesh. Then I can add a geometry proximity node and grab the distance to this mesh from the points. Again, to adjust the gradient, I add a map range node and set this from max to 0.1. If you want a soft fall off, you can increase this a bit. I keep it at 0.1 and swap these 1 and 0. Now we can just plug it to the mix factor here. But I like to use this fall off we made earlier with this mask. So I put a multiply node and multiply those two together. Then plug it to the mix factor. Now when I refresh the sim, bugs only avoid areas actually lit by the light. If you want, you can link the light data such as distance and intensity to the hard-coded values inside the geo setup using drivers. Copy the driver from here and paste it where you want. But that's for another tutorial. You can even add a switch node to toggle between proximity mode and this Raycast mode, depending on what you need. Also, increasing the sphere resolution will give you a better results. 64 is enough for most cases. And that's it, our bug simulation in Blender, done entirely with geometry nodes. As always, thanks for watching and I'll see you in the next one.